Muy buenos días, estimados amigos de toda Latinoamérica. Les saludo desde Lima. Tenemos la conexión para la siguiente conferencia a cargo del doctor Yury V Murashov desde San Petersburgo, Digitalización en la Ingeniería Eléctrica. Un saludo para los participantes desde la Universidad Autónoma Metropolitana Iztapalapa y al resto de participantes. Entrego la palabra entonces al doctor Yury Vasilievich Murashov. Здравствуйте, я короткое представление давал нашей аудитории. Присоединился
Добрый день, доброе утро.
И спасибо заранее. Даю слово.
Good afternoon, dear students. So, today we'll speak about digital technologies in the industry, energy industry, of course. And if we'll speak about this one area, first of all, we must understand what we can think, what we can understand when we can speak about digital technologies. When I speak about this one area, of course, first thing or first dream maybe, it's a simulation of different physical processes. Not only physical, different technological processes and control processes in the energy area. So if we'll speak about this one area, first of all, we must speak about different laws which we will use for the simulation of different physical processes. And we must discuss which one, or maybe few problems, or maybe there are a lot of different problems which we have in our industry, not only in the world industry, energy industry. So we can start, and first of all, it's modern problems of electric power industry and electrical engineering. And first of all, it's typical problem with electrical contacts. If we speak about thermal state, if we speak about lighting protection, breakdown problems, of course, it produces a lot of different crashes, which sometimes really negative. If we speak about the full energy system, and of course, we must predict a lot of different problems. And one of the general aim for all engineers, it's creation of different energy equipment which produce and give us possibility work in future without problems of safety. So if we'll speak about this area, of course, we must know some fundamental laws. And first of all, it's Gauss law, electrostatic. It's a general law applied to any closed surface. It's an important tool since it permits the assessment of the amount of enclosed charge by mapping the field on the surface of enclosed charge by on the surface outside the charge distribution, of course. So if we speak about different geometries, for geometries of sufficient symmetry, it simplifies, of course, and the calculation of the electric field will be really simple because it's possible to use axial symmetry or another one symmetry. Sometimes it gives us possibility to evaluate different results by analytical function, and of course it's really comfortable because it's not necessary to use some specialized software, for example, and it gives us possibility to evaluate different tasks with a really big tolerance, of course. So if we speak about another one law, of course it's the Gauss law, but another one view of this one law. So if we speak about this one, if it's necessary to use some special software, of course, it's necessary to create a differential form of Gauss law from integral one. Of course, we can use Strogarsky-Gauss theorem for it. And here you can see final version of this one law. And this one law we will use as the first Maxwell's equation in a full system of 4 equations. And of course, it's necessary for simulate electrostatic task. So another one is the same one, really close to the previous one. It's magnetostatics law, Gauss law, another one, the second one. And of course, we have the same one approach, but for magnetic flux, for magnetic field. we will go from the integral form, which well known even over the world, to differential form, which we will use in different equations in future. So if we'll speak about another one, it's Faraday law. And of course, it's a really important law because it gives us possibility to connect electrical field with magnetic field. And of course, this law, it's really important for us for investigate different physical processes. And here you can see some common equation for this law, and of course we can produce also integral form, which give us the third one equation in our system. So if we'll speak about the last one, of course it's Ampere's law, and of course it's also really important law. But if we'll speak about the usual form which we can produce from the integral form, common form, it will be not enough, because this one law don't give us possibility to evaluate different processes inside capacitor, for example, because we have the electric inside in between two different plates, and of course it's not possible to predict, it's not possible to use this law, for example, in this one form, short form, differential form, first one, for their explanation the work of capacitor. But if we'll add some additional parts of this one equation, of course it will give us possibility to evaluate not only for conductor systems different distribution of current and magnetic flux, for example. It gives possibility also to use this one equation for dielectric materials. And of course, it gives possibility the full form of Maxwell equation. Here you can see the usual one. First of all, it's of course integral one, and another one is point form, which you can use for different tasks if I speak about electromagnetic tasks. And of course, this one form will be really comfortable for you in future if you will use for pulse or time-dependent task, for example. Of course, it will be necessary to use it. But if we speak about another one view, for example, it's for harmonic form, time harmonic form. It's comfortable when you have periodic function. For example, if we speak about alternative current system, it's necessary to understand the simulation time. For example, if you have a really short time of simulation, which really close with a period, for example, of this one function, it will be necessary to use point form. But if the time simulation is really big, more than 5 periods, for example, or 10 or more, of course, it will be more comfortable to use time harmonic form for the explanation of different processes in the system. So, but if we speak about good engineering, it's not enough, of course, to know only this equation. And of course, it's not enough for predict different problems in power industry. Another one part of your knowledge, of course, is heat balance equation. And this one heat balance equation is really comfortable for explanation of different parts of usual differential equation. So, and if we'll speak about this one of the most important law, it's some kind of energy balance equation when we have input energy and output energy. So, and the same one method we can use for this one. We have input objects and output. For example, we have heat source. If we speak about electrical system, it can be Joule heating, for example. Also, we have losses by radiation, for example. Also, we have conduction, for example, for solid materials, and also convection, if we speak about different liquids or gases, for example. So, if we'll speak about this one equation and what we must have for the correct solution of it, of course, first of all, it's a boundary and an initial condition. So, if we'll speak about boundary conditions, first of all, it's Dirichlet boundary condition. It means that we know the fixed value of temperature, or it can be some kind of function, but it's not a differential part of temperature. It's a usual value of temperature or any function or distribution of temperature along this wall, for example. If we'll speak about surface temp, if we'll speak about surface, it's necessary to identify the distribution of this one. Well, and of course, sometimes it's really rude boundary condition, and so not really comfortable for explanation. For example, if we'll speak about combination of different materials, it's not possible to use this one law, because usually we must work with another one, name and boundary condition, when we speak about heat flux density, for example. Yeah, because usually when we speak about different communication between different materials, between different objects, for example, it can be solid and gas, for example, or liquid, for example. And of course, usually we need to use heat flux density for it. And if we speak about name and boundary condition, it's this one, heat flux density, of course. It's differential part of temperature by coordinates. Yeah, and of course it's possible to apply this one for different tasks. And today we'll speak about this too. I'll show you different usual task, which we have in power industry, for example. Yeah, and we'll show you how you can use these laws for the explanation of your model, for creation numerical model, for simulate and create some kind of digital solution, or maybe digital twin is something excellent part. Yeah. So if we speak about another one variant of boundary condition, but it's really close to the previous one, it's convection boundary condition. If we speak about the left part of the equation, which you can see on your slide, for example, yeah, of course, the differential of temperature by coordinate, of course. And if we speak about the right part of the equation, it's Newton-Riemann equation with the heat transfer coefficient. Yeah, this one heat transfer coefficient, it's possible to identify from different handbooks, for example, yeah, or maybe from experimental study also. Sometimes it's possible to evaluate from analytic evaluation of this one coefficient. So, and if we speak about the next step, it's interface boundary condition. As I said before, sometimes it's necessary to create the combination of different materials. For example, you can use isolated material or non-isolated materials. You can connect it together, for example, or connect to different materials with different properties, of course. And as I said before, we need to identify heat flux density from the one material to another one. And of course, it's ideal form of this one when temperature from the one side of materials is equal to another one side from another one material. Yeah, but it's ideal, of course. Sometimes it's not possible to use this equation. For example, when we speak about electrical contact, or if we speak about real materials, of course, we have some problems with surface because it's not ideal, and the communication between these surfaces usually only in few points, not used all surface, for example. It's one of the reasons why sometimes this equation will give not correct result. And of course, it's necessary to know about it, because sometimes it's not possible to verify or validate your results if you'll use this one equation. But of course, I'll show you how it's possible to use another one example. For example, when we speak about electrical contact system, I'll show how it's possible to use different equation for organize the communication between different contacts and evaluate correct temperature distribution inside the contact, because sometimes it can be really important. Because if I speak about typical example, yeah, it's only few degrees, but if I speak about critical, sometimes it can be 10 or more degrees. Yeah, and of course it's not possible to use only this one equation for some contacts. So, and finally, if we speak about the solution of differential equation, yeah, and different condition, of course it's initial condition. Of course, when we speak about evaluating a different system, we must know the beginning of the beginning state of this one system. For example, if you want to evaluate the temperature distribution inside your classroom, for example, yeah, after 1 hour, it's necessary to know the initial temperature or initial distribution of temperature inside your classroom. Of course, you must also give some boundary condition. For example, it can be temperature on walls, wall temperature, for example, or it can be some kind of distribution, or maybe you know some information about heat transfer coefficient, or maybe you know some heat flux density through the walls or through the window, for example. Yeah, and of course it will give you a possibility to predict the temperature distribution inside your classroom after 1 hour. And of course you can use for this one task heat balance equation or temperature balance equation. Yeah, but if we speak about this one example, classroom, yeah, of course it's not enough, because we also must take into account the convection process inside the classroom for correct evaluation of distribution, of temperature distribution. Yeah, and for this we must use Navier-Stokes equation. For example, you can see it here. This one is for the laminar flow, and here you can see this one equation. Yeah, but if I speak about this one equation, it's not full, because if I speak about this one, yeah, we have two variables, its velocity and pressure, in one equation. It's not possible to evaluate the solution of this equation. So, but it's possible to add another one, this one continuity equation, which gives us possibility to find final solution of this system of equation. Yeah, but of course it's not easy to find the analytic solution. If we speak about common form for this one moment, it's not possible. But you can tell me that there are a lot of different people in our world who evaluate different system distribution of velocity, pressure into really difficult systems, of course, without any problems, or maybe without any problems. Yeah, but usually, not usually, in every one case they use some special software with a numerical method, numerical simulation method, and of course we'll speak about this software too. For example, if we'll speak about maybe the most famous software in all the world, first of all, it's MATLAB Simulink. Usually it gives us possibility to solve different mathematic system, and of course it gives us possibility to simulate different physical processes. It's possible to simulate inside MATLAB, or it's also possible to simulate another one super package, for example, in Simulink. Yeah, and of course it's really comfortable if we speak about Simulink to simulate, because it's usually not necessary to know any languages of programming. Yeah, because it's possible to create block scheme for the simulation and find the final solution. But if we speak about MATLAB, usually we need to know MATLAB language for coding, for programming. Yeah, and of course sometimes it's not really comfortable. But if we speak about this one software, it gives us wide possibilities. And of course, if we speak about this one, it's really powerful software. So don't forget this software, because it's really important. And of course, it's necessary sometimes to work with software, not maybe only this one. Maybe it's possible to work with any combination. For example, one of these combination can be organization of combination between MATLAB Simulink and COMSOL Multiphysics. For example, today we have international webinar of COMSOL Multiphysics and collaboration of COMSOL Multiphysics with MATLAB and Simulink. And of course, it's really comfortable, and it's really important collaboration, because if I speak about COMSOL Multiphysics, of course, from the name of this one software, you can understand that it's prepared specially for the simulation of different physical processes. But if I speak about this one, sometimes it's not enough if we speak about possibilities of this one software. For example, if we'll speak about different interpolation, different evaluation of different equations, for example, sometimes it's more comfortable, or maybe it can be only one way to find the solution inside MATLAB, for example. Yeah, but it's possible to use a live link between these two software for the organizate the collaboration between these softwares, for example. Yeah, but if it's about COMSOL Multiphysics, of course, it's really interesting software. It's really friendly software for different users, because sometimes it's not really difficult, because it's not necessary to use some special language to speak about programming, but of course it's necessary to know different physical laws and understand how it works, and also sometimes it's necessary to understand find element method and different solvers, different configuration of solvers for their solve different differential equation. Yeah, and of course, if I speak about this one software, it gives us possibility to evaluate a lot of different tasks in electrical engineering sphere. Yeah, in electrical engineering area. Yeah. So, but if we speak about usual simulation of different power source, for example, yeah, for my opinion, it will be more comfortable to use Simulink, MATLAB Simulink, of course, with special libraries for the simulate different power sources or different transfer processes in power grid, for example. Yeah. But if we speak about thermal state of power source, or breakdown inside power source, or maybe arc welding process, or for example something like this, yeah, arc extinguishing, arc ignition process, of course it's more comfortable to use COMSOL multiphysics. For this one moment, you can find a lot of different webinars, a lot of different materials how we can use this software. So, but also there is another one software, it's ANSYS, which you can see here, for example. One of, for example, it's Fluent, usual one, yeah. And of course, if I speak about this one, it's for some tasks, it will be more comfortable, more correct. For example, if I speak about simulation of computational fluid dynamic tasks, of course, it will be more comfortable to use ANSYS, because it gives possibility to find solution with smaller configuration of your PC, for example. Yeah, because if I speak about RAM memory for the same one task which you will use in ANSYS, it will take, for example, few gigabytes. If I speak about COMSOL multiphysics, usually it take 2 or maybe 3 times more. Yeah, RAM memory, and of course sometimes it's not really good. So for the slightly different physical processes. And another one advantage of COMSOL multiphysics, if we speak about this one software and compare with ANSYS, of course, it's possibility of simulation multiphysical processes. Yeah, because if we speak about ANSYS, sometimes it's not really comfortable to simulate computational fluid dynamic task for the thermal state of electrical motor, for example, yeah, and simulate this one electrical motor and the same one moment. Because if we speak about ANSYS, usually we use Fluent for the simulate of heat transfer process, yeah, and computational fluid dynamic process, yeah. And if we speak about simulation of electrical motor, it will be another one package of this one software. It will be Maxwell, and it's Maxwell. And of course, it's not so easy to combine together. Well, if I speak about COMSOL multiphysics, it will be possible to do it in one area, in one graphical user interface, and of course, it will be really easy, and of course, it will be more comfortable than if we'll use ANSYS, for example. Well, but if we'll speak about these 3 different softwares, MATLAB Simulink, COMSOL multiphysics, and ANSYS, of course, you must have license of it. But of course, it's possible to buy really cheap license. It's for study, for education, and I'm sure that if you speak about your university, you have access to MATLAB Simulink, and also you have access maybe to maybe for COMSOL multiphysics, or maybe ANSYS, or maybe for these 2 software in one time. So, but if we speak about alternative one software without any license, it's open form. But if we speak about this one software, it's possible to use this one only if you will use Linux operational system. So, of course, it's one of the most disadvantage of this one system, because if we speak about usual customers in over the world, yeah, usually they use Windows, and of course, sometimes it's not comfortable. So, but today we'll speak about COMSOL multiphysics, and I'll show you how it's possible to use this one software for electrical engineering. So, and first of all, it's necessary to understand what we have inside the component physics. First of all, it's the general products, general part of the component physics which give us possibility to solve differential equation. Well, and also, if we speak about this one software, we have a lot of different special interfaces. Well, and of course, if I speak about this one part, maybe I'll show you which one is more important for you as electrical engineering or specialist in electric technology processes. So first of all, it's of course it's AC/DC model. Yeah, if you will evaluate different arc processes, it will be necessary to work with plasma. It's possible to combine together, of course. So also, as engineer, you must know structural mechanics. Maybe not fully but some part of this one area of science you must know, because if we speak about usual electrical equipment, of course, it's necessary to use some understanding of different mechanical processes. Yeah, because if we simulate electrical contacts, for example, yeah, you must know how it's possible to evaluate pressure between these contacts. You must know how it's possible to find the distribution of this one pressure. Yeah, and of course, it's necessary to understand how many commutation you can produce of these contacts if we'll speak about mechanical resource. Yeah, but if we'll speak about another one part of this interface, of course, it's computational fluid dynamics. Maybe it's not really often, but if we'll speak about different convection processes, for example, you would like to simulate heat transfer process for your computer, for example, or for semiconductor devices with heat sink, of course, it's necessary to know some aspect of computational fluid dynamics. It's necessary to know how it's possible to simulate, because if you will use correlation models, of course, it's possible to use correlation models, and also you will find already prepared correlation models of different convection processes inside conformity physics. It's not really big problem. But if we speak about this one area of computational fluid dynamics, it will give you possibility to correct it with bigger tolerance. Yeah, because sometimes it's necessary to evaluate with a really correct results with really big tolerance. Of course, it will be more correct if you will use computational fluid dynamics. Because if we speak about correlation models, usually we use different empirical laws. And for this one moment, if we speak about electrical engineering area, of course, for different parts of electrical equipment, a lot of different engineers usually use empirical function for evaluation of different processes. It's possible to use empirical function, of course, but for my opinion, it will be possible to use for the first step of creating something new. The next step, of course, from this one previous evaluation, you must create some kind of geometry. You can understand in which area you can change the parameters, geometrical parameters of your object, for example. Yeah, and after that you can create parametric sweep simulation study. Yeah, which give you possibility to identify optimal parameters of geometry of some object, for example. Yeah, and give you possibility to identify correct schemes and how it's possible to create. And of course, it's possible to do from the first one step without simulation, but it will take a lot of time, because it will be necessary to produce a lot of different experimental studies. Yeah, experimental investigation. And sometimes it will be really expensive. So, or if I speak about numerical simulation, of course, it gives you possibility produce the same one experimental study, but with smaller cost, for example. Yeah, but not every time, for example, because sometimes it's more comfortable to produce the experimental study, not this numerical simulation. So if we'll speak about another one possibilities, of course, it's optimization model, as you understand from my previous part of speech of optimization of geometry. Of course, sometimes it's necessary to use this one model for it. Also, another one really important part of this software is material library. If we'll speak about popular materials, of course, you will find all of these properties inside this one library. but sometimes it's not enough. For example, if we speak about electrical engineering, we have copper, but if we speak about this one library, we have copper, but the properties of this material doesn't depend on temperature, for example. Yeah, and of course it's not comfortable, because if we speak about simulation of heat transfer processes, it will be necessary to use the material with properties which depends on temperature, of course. But it's not really a problem, because it's not really difficult to create your own material with the properties which will depend on temperature, for example. Yeah, but of course, if we'll speak about some tasks, it's not necessary to use. For example, if we'll speak about electrical motor simulation, sometimes it's not necessary for first one step identify the losses inside the electrical motor, for example. Yeah, and of course it's one of the reason heat losses, for example, or something like this. Yeah, sometimes it's not necessary to simulate these properties which will depend on temperature, of course. So, but for some tasks, as you can understand from previous my speech here, it's necessary to know this. So, another one part, of course, is different live links. Previously, I said to you that we have live link for MATLAB, and of course, it's really big advantage of the software. Another one advantage, it's CAD import model, which gives us possibility not only import the geometry, it gives us possibility change ready prepared geometry in AutoCAD, for example, or SolidWorks or something like this, yeah, and change inside consultative physics. And also there are a lot of different additional links for different CAD softwares, which give us possibility not only change the properties of different or parameters of your geometry, for example, yeah, it gives us possibility to organize some kind of feedback from the consultative physics to this one software, CAD software. Yeah, it gives us possibility to, if you identify that optimal parameter of your geometry has this one value, for example, it's not necessary to rebuild your model inside the SolidWorks or Inverter of AutoCAD and change all schemes, for example. It will be enough if you organize the connection between consultative physics, and consultative physics will produce these changes automatically. And of course, it's really big advantage for engineers. So, but if we'll speak about the simulation of partial differential equations inside the consultative physics, first of all, we must know that we have three different forms. First of all, it's coefficient form, more usual for Russian Federation and our students, general form, and weak form. So if we speak about coefficient form, you can see this equation here. Yeah, typical example of this one is temperature balance equation. Yeah. So if we'll speak about general form, it's some kind of coefficient form with some small parts which include the full one from this. Yeah, and of course, it's not sometimes not really comfortable to understand, because it's necessary to remember about all parts of equation and so necessary to remember about all coefficients. Yeah. Well, if we'll speak about weak form, it's more comfortable if you will use MATLAB. Well, and of course, it's really comfortable to use this one software, this one form of equation. It will be possible to adaptate your model for working in MATLAB and organize the collaboration between consultative physics and MATLAB. But of course, if some kind of advice, maybe it's not to use different PD interfaces, because consultative physics has a lot of physical interfaces which already prepared for you, and it's necessary to use these PD interfaces only in one case, if the already prepared interface, physical interface, doesn't give you possibility to work with your lore or something like this. Yeah. So, and the first one example, it's instigation and numerical simulation of contacts and current carrying systems and thermal states of this system, of course. So if we'll speak about this one, there are a lot of different examples where we can find this one task in over the world. Of course, the first one example, it's usual circuit breaker, maybe one of the most famous electrical equipment over the world. It's well known not only for electrical engineers, for usual customers, it's also well known. Different switches or disconnectors, also vacuum breakers, and also different usual contacts. Yeah, of course, it's necessary to know how we can simulate it, because it's necessary to know their thermal states for safety using. Yeah, and of course, the most problem of it, Joule heating, which produce a lot of different problems for different parts of these devices. So if we'll speak about Russian standards, you can find in this table, and it's not necessary to take a lot of time for consider of these values. I think it's really close with your standards, because our climate not really close with your, for example, but if we'll speak about south part of Russian Federation, of course, maybe it will be really close with you. And it's one of the reasons why these standards, it's maybe not the same one which you have in your country, yeah, but it's really close with you, with your standard. So, but when we speak about application, for example, if we'll speak about the usual solution of different temperature distribution in bus bar, of course, it's not really difficult task, because usually we have Fourier law, which gives us possibility to find analytic solution of temperature distribution in different bus bars. Yeah, but it usually works only for simple geometry. When we speak about different geometries, about difficult geometries especially, yeah, with the different isolation, with different convection parts, of course, different convection processes, sometimes it's not possible to relate analytical function of temperature distribution inside bus bar. And in this one task, in this one case, it's necessary to use numerical simulation. So one of the example, for you can see usual circuit breaker for nominal current 1 kiloampere, or maybe more. I don't remember exactly at this one moment, but it doesn't matter. So with short circuit current more than 100 kiloamperes. And of course, typical task for the first step of evaluation of geometry, it's identification of thermal state of this contact system. So, and in this one variant, we can see that we have the following approach. First of all, if we'll speak about perfect contact, thermal temperature of one surface is equal to another surface of another one material. You have some kinds of balance equation, yeah, and of course temperature will be connected in one point. But in the real one contact, as I said before, we have some problems with the surface, and we have connection only in few points, yeah, and of course it will be not ideal contact, and temperature of one surface will be quite different, yeah, than for example, and here you can see the graph of this difference between the temperature from the one surface to another one. And of course, it's not possible to use this balance equation. So we must add some additional part for this system, yeah, with some kind of source of heat, yeah. And of course, we must take into account characteristics of these surfaces. So, but how it's possible to take into account? There are a lot of different models of different contact system. For example, the most famous for this one moment and more usual, if we speak about simulation, is Cooper-Mikic-Ivanovich model. Yeah, it's if we speak about plastic deformation model. Of course, there is also another one model. It's Ivanovich model. Also, there are a lot of different models. For example, for this one moment, I remember more than 20 or maybe 23 models of electrical contact. But from my experience, I can say I can tell you that the Kupernik-Ivanich Laplace deformation model, one of the best for this one moment. And if I speak about typical system of different contacts, it gives really good results. And of course, it's one of the reasons why we will use this one also Kupernik-Ivanich model for the identification of heat transfer coefficient and current transfer coefficient between one surface of the contact, from the one contact to another one contact, yeah, from one surface to another one. So if we speak about this one is heat transfer coefficient, yeah, and here you can see some kind of equal electric conductivity between these surfaces. Also, you can see some parameters of surfaces, yeah, from previous one slide. Yeah, you can see here. Also, you can see that we need to know the pressure of contact pressure, yeah, and of course it's necessary to use this one parameter. Well, I have forgotten how it's in English. Well, well, maybe, yeah, hardness, Brunel hardness, for example. It can be Brunel hardness, Vickers, or also micro hardness, for example. Yeah, but of course it doesn't matter, because if we speak about COMSOL multiphysics, it's necessary to choose only that parameter which you will use. For example, it can be Brunel hardness, yeah, and put the value, and of course it's adapted for micro hardness or Vickers hardness, or from one to another without any problem, because all correlation or equation between these hardnesses, yeah, we know it's well-known function. Of course, it's really comfortable to use it for identify correct distribution. So if we'll speak about this contact, of course, it's necessary to evaluate material properties first of all. This one, it's not really simple case, because if we'll speak about the contact surfaces here, it's from composite materials, which include silver, for example, yeah, and of course, if I speak about this material, and so also it's not really simple, because it has some kind of porosity. It's also necessary to take into account the properties and find the correct solution of it. And of course, if I speak about porosity, for example, you can see that we have for 20%, yeah, and also evaluate different properties, and here you can see the dependence on temperature, yeah, which we'll using for only these contacts. If we speak about other parts of this circuit breaker, of course, it's copper and some composite material which doesn't provide electrical currents. It's not necessary for this one task. It's necessary only for heat transfer test when we speak about the insulation material, yeah. So if we'll speak about this typical task, of course, it's necessary to take electrical current, physical interface of COMSOL multiphysics, the equation you can see here, yeah, and also you can see the temperature balance equation. For example, you can see that in this one part of equation we have only conductance part without any convection. It's one of the reason of this one. It's not mistake. In this one model, we take into account only the geometry of contact, and we don't take into account the surround air, for example, yeah, or another one material, yeah. We didn't take into account it because it's not necessary for us, because all correlation models gives us correct result, and for us it's not necessary to know the temperature distribution inside the air. It's more important for us to evaluate temperature distribution only inside contact system. It's one of the reasons why it will be more comfortable to use different correlation models. So if we'll speak about this task and this equation, of course, it's connected together. First of all, we have Joule heating, which produce currents which carry inside the system, which flow inside the system. And here you can see this Joule heating, which will go from this system equation. But if we'll speak about this one equation in feedback, for example, yeah, with previous one, it's temperature balance equation. also connected with electrical by properties, because if we speak about electrical conductivity, it depends on temperature. Yeah, of course, it's one of the reasons why it's necessary to know the real temperature distribution. So these two equations fully coupled, yeah, fully connected between each other. It's one of the reasons why it's not so easy task for the solution. And here you can see some simulation result. Yeah, first of all, it's some stationary process. Yeah, if we will use stationary solver, yeah, it's fixed value for infinite simulation, for example. Yeah, also we have some experimental data. Yeah, and also we have some simulation result, blue line. Yeah, and you can see that it's really close with experimental data. Of course, if we'll speak about dynamic process, we have some difference between the simulation result and experimental data. But these problems and these mistakes from the correct value or incorrect value of heat transfer coefficient, because heat transfer coefficient depend on temperature gradient, and of course it's one of the reasons why it's not why it's necessary to take as function and evaluate it correctly inside COMSOL multiphysics. And if we will produce this one function, of course it will be more correct and the evaluation will be more correct. But if we'll speak about this one coefficient, it's not really simple to find. It's one of the reasons why we use constant value, and here you can see the simulation result. So after the verification of the model or validation of model, if we speak about comparing with experimental study, of course it's possible to produce with parametric simulation. It's really comfortable because you must put some parameters only, and after that only control the results. Yeah, and here you can see that we use different values of currents for different ambient temperature values. Yeah, for 20, 40, and 70 degrees, Celsius degrees, of course. Yeah, and after that evaluate the temperature of our contact system, and after that we can understand for which one ambient temperature with which one current we can use our system. So some kind of conclusion maybe. Yeah, first of all, non-stationary three-dimensional mathematical model of heat transfer processes of the high current AC circuit breaker contact system is developed. The mathematical model includes Cooper-Markic-Ivanovich correlation. It's correlation between the contacts, not only heat transfer coefficient, it's take into account also electrical, some kind of transfer coefficient, yeah, from another one part of contact to another one, yeah. So also you can see that we evaluate the composite material properties, which depend on temperature. Of course, this calculation was produced in MATLAB because some positions were not really comfortable to produce inside COMSOL multiphysics. So if we'll speak about experimental studies, it were performed to verify the more mathematical model or validate. It will be more correct if we'll speak about the some words. Yeah, so if we speak about the numerical simulation results, it's confirmed by experimental data, of course, and the absolute area does not exceed 4 Celsius degrees. If we speak about dynamic process, yeah, and doesn't exceed 1 Celsius degrees. If we speak about stationary process, you will see it's smaller than 1 Celsius degrees in stationary state. After how much I can see, after 10,000 seconds it will be in stationary mode, in stationary state, for example. Yeah, so another one example, maybe widely used in our the world, in our small countries, for example in European countries, it's investigation and numerical simulation of a closed transformer substation thermal state. Well, a typical problem which we know for ABB company, that they use previously they use only empirical function for evaluation of thermal state of substation. And of course, it was really big mistake for them because when they decided to produce the transformer substation for Egypt, for example, yeah, they have a lot of different problems with temperatures, and it's one of the reasons why they asked us to evaluate thermal state of transformer for them and to evaluate correct losses of transformer, evaluate correct distribution of temperature inside the area, inside the volume of transformer substation. Yeah, and here you can see some of typical examples. For example, the left one, yellow one, yeah, typical transformer substation which we have in Russian Federation. Yeah, but if we'll speak about some special solution, yeah, for different European countries, it's the right part of the slide, and also for some not really comfortable regions. For example, this one transformer substation can be used for Alaska, for example, speak about USA, or it can be used for different north part of Russian Federation, or sometimes it's necessary to use in some specific situation, for example, for military. Yeah, and of course, it's also necessary to evaluate correct thermal state of this transformer substation, because it's necessary to produce correct condition for work of transformer. So, and when we speak about the simulation of transformer substation, of course, first of all, it's necessary to understand how you will simulate transformer. First of all, you can simplify your model, and also you can use detailed model, yeah, detailed geometry. Well, and of course, it depends on your aim. If you would like to simulate distribution of temperature inside the substation, transformer substation, yeah, and it's not necessary to take into account this temperature distribution of transformer, of course, it will be better to use simplified geometry of transformer. But sometimes it will produce an incorrect result, because sometimes if we speak about small volume of transformer substation, it's really important to know temperature distribution inside transformer. And it's the same, not the same, it's really important case when you can understand that first of all, you must sit and think about how you will simulate it. If I speak about usual engineering solution, of course, it's will be more comfortable to simplify it, to simplify your geometry, for example. Yeah, well, but it's sometimes it's not correct solution, as I said before, and it's one of the reason why maybe it will be more comfortable to produce few models. First of all, detailed, which take into account only information about transformer and correlation models if we'll speak about surfaces of transformer, yeah. And after that, this solution, this power distribution, this energy distribution, take from this one model and import to your model transformer, and put this one transformer inside some kind of box, yeah, where you will try to simulate different convection processes, for example, yeah, heat transfer processes with convection. So if we'll speak about this one, detailed geometry, well, there are few different possibilities how you can evaluate losses. Of course, there are a lot of different empirical functions, empirical methods, and of course, it will be possible to compare the simulation results with some parts of simulation result with this method of relation, empirical method. So first of all, some information about this one transformer. We have three-phase transformer with this one full power, yeah, and with this first winding voltage value, yeah, and the secondary winding with this one connection, yeah. So also we have number of coils, number of turns for the primary coils, for the secondary coils, yeah. And of course, it's necessary to take this into account. So if we'll speak about simulation of this one, of course, we must create the geometry, and it's really important part, because if we speak about the simulation of coil inside the console multiphysics, you have two different approaches. For example, it can be a multi-tone coil domain or single-tone coil domain. And for this one case, when you have a lot of different tones, a lot of a really big number of tones, of course, it will be more comfortable, more correct to use multi-tone coil domain. And also another one important part, of course, is simulation of your core, transformer core. As you know, we have plates of steel which connect together, and so we have insulated material between them. And of course, it's not really simple to simulate it, and of course, it's not comfortable to create inside different software. So it doesn't matter, because it's possible to create full geometry as one solid body, one full body, for example, and to use laid material properties for the final solution. So, and if we'll speak about the simulation,